Okay, before I do a little bit more with logarithms, let's just quick re-sketch what a log graph looks like. Sometimes I find, this is just the way my brain works, in order for me to fully understand logarithms, I always have to either go back to what a log graph looks like, or before I even do that, sometimes I have to remember that a logarithm is really an exponent graph that has been modified so that we can get the exponent by itself. Does that make sense? So just quick recap of logarithms. If you have, this is an XY axis, a graph that looks like this with an up and down asymptote and then slow growth, that's a logarithm graph. Okay. A few unique properties of logarithms. You cannot logarithm a negative number. I don't know what the verb is.
Sorry, Tom.
Yeah.
I'm just making sure. Are you recording?
Yes, I am.
Okay.
You cannot logarithm a negative number. Okay. It's just not something you can do. Like x, like you can't take the log of -2. That's just not a possibility. Does that make sense? Okay. Another thing is, though, you can't actually log 0. The log of 0 is also something you can't do because as you look on this graph here, it never actually touches 0. Now, the answer for a logarithm, however, can be a negative number. So, for example, like right here, you can have a negative number be the y value from a log. If it helps, sometimes I have to remind myself, and don't feel bad if you have to do the same thing. A logarithm is really an exponential graph that has been inversed and flipped over this diagonal line of y equals x. The whole reason why logarithms were developed, I like that word, is we needed to try to find a way to make it so that if you have x equals 2 to the power of y, that we have a way of rearranging that equation. Let's rearrange that equation. If I give you 4 equals x to the 7, how do I rearrange this particular equation into a logarithmic form? Do you guys remember?
Base.
Log. Then you base the x. This base right here is this little base right here. Then the 4 is actually what you are going to logarithm. Again, I don't know what the verb is there. But the real point of this is that this little exponent up here that you weren't able to get by itself, now it is by itself. Okay, I used the example of a toolbox earlier. This is a skill I hope you guys will have if you don't already have this skill at some point. But one of the other skills I need you to have is knowing when something is useful or not. Let's say I wanted you to solve for x. Would changing this into this format be helpful in solving for x? No. Because if you wanted to solve for x right here, I would just take the 7th root of both sides, and that would get you x by itself. So one of the things I'm going to need you guys to work on over the next week and a half is when are certain skills helpful? Because you might be able to do something, but maybe that's not actually purposeful in helping you solve your problem. Okay, here are the laws of exponents. We're actually then going to take some of these laws of exponents and change them into laws of logarithms in the next slide. So, do you guys remember how did these exponent things work? Should I take much time on these, or? Okay. So, similar to laws of exponents, logarithms also have rules. And basically they function in a very similar manner. If you have things that multiply corresponds to add. If you have things that divide corresponds to subtract. Does that make sense? The first two laws are almost the exact same as some of the exponent laws. Like, see how here multiply becomes add and divide becomes subtract? That's how these first two laws work. You just need to make sure you use them properly. Okay? So you need to have the m and n multiplied by each other inside the bracket. And then if you wish, you can separate them into two individual logarithms. That's a rule that you could use if it helps. Okay. This rule right here, the third one, is known as like the power rule. And basically the way it works is that if you ever have an exponent, it's actually allowable for you to take that exponent and throw it in front of the entire logarithm. And this is also, again, a rule that in some cases could be helpful. It's not always helpful, but it could be. This one's the power rule. This one is known as change of base. And basically the way this works here is that if you have a logarithm written with a base down here that you're not exactly fond of, what you could do is you could actually divide two logarithms by each other, so long as the new logarithms that you have the same new base. Usually the new base we go with is 10, by the way. So these are the rules. Let's do a bunch of examples. That's like the best way of doing this. So these are not probably what you'd get asked on a test, but I just kind of want to start with something that's maybe I want to put numbers in. So log 15. I'm going to say this a lot over the next day and a half. If you ever have log of a number, it is just a number. Like log 15 is 1.92 something stupid. It's probably not 1.92, but like it's just a number. Does that make sense? However, we could write this as the sum of two logs. See if this makes sense. Log 15 could be written as log 3 times 5. See how I'm keeping the 3 times 5 though in a bracket? Well, this is now the first logarithm rule that I had on the previous slide. You have two things multiplied by each other. This should be equivalent to log 3 plus log 5. And if you don't trust me or whatever, you should be able to test this, right? Like in your calculator, type in log 15. It is just a number. Then go and type in log 3, like close the brackets on the 3. Type in log 5, close the brackets on the 5. It should be equivalent. Does that make sense? How about this one? Right, log 6 is the difference of two logs. So why don't we write it as, like, say, log 12 over 2? Does that make sense? Because 12 over 2 would be, like Sean just said, for division, that would be equivalent to 6. How do I break this up, then? Oh, want to take a stab at it? Well, what we just do is we do log 12 divided by log 2. Okay. Now, I should make a point here. This is not equivalent to log 10. That's not how logs work. You can't just take this 12 right here and this 2 right here and say they're equivalent. This is a number. This is a number. That number should be equivalent to log 6. Okay. And it's based on the fact that logs are really an extension of exponents, and that's how exponents work. Okay, so let's try this next one here. What is log 4 plus log 3 equivalent to? Good, it's log 12. Why? Well, these guys are added. Separately added, they can be collectively multiplied, so 4 and 3 is 12. And again, if you want to, like, I guess you guys don't seem to care, you trust me, I guess. But you should be able to test this in your calculator. So what about this guy? Okay. Now don't forget though, it needs to still have the base of 3. So that's a little detail I want to point out here, is that these guys right here have a base of 3, so it should still be a base of 3. So whatever 4 times 2 times 3 is 24. Don't forget, log base 3 of 24 though is just a number.
How do you do base 3?
Depends on your calculator. You need to go into, when you have a calculator here, you've got to go second catalog, and then you've got to go all the way down till you get to L. So I press this button here to get you to L, and then hopefully yours does it, where you get like, mine has log in the list there, but hopefully yours has like a log with a little base. That's how you do the 3. If not, the way that we're going to learn actually a little bit later today, there's a change of base rule that says this is actually log 24 divided by log 3. That's actually the other way you can type it in your calculator. Can you find that? So we just need to go far enough. I'm going to press this button here for L. Down to the L's. Okay, you don't have one yet. So you got to go log 24, and you have to divide by log 3. That's how you do it. Okay. Do you guys see how for the next two ones here, I've used different words in italics? I just want to point out the difference here. Simplify would just mean let's find what this is equivalent to, still with logs. So like for example, you're going to do 20 times 3, which will be 60. But then you're going to divide by 15. So this guy right here would be the log of 4. Does that make sense? So you're going to do the 20 times the 3. But then because of the minus sign, you're going to divide by the 15. So I guess if you wanted to, you could write it as the log of 20 times 3 all over 15. But that's log 4. Okay. This one right here, when I said evaluate, this should actually hopefully be equal to not just a number that's like an ugly decimal number, but hopefully this guy right here is equivalent to something we can solve for. For example, this is going to be a log base 2 of whatever 384 divided by 12 is. Can someone help me out with that? 32. Does that make sense so far? We can go further than that though on this particular one. Now you can just type log base 232 in your calculator. What you also could do is you could say if I'm going to evaluate it, it's going to be equal to x. Like I'm trying to solve for what this is equivalent to. Here's my toolbox analogy again. There is a tool that's very useful in solving a problem of this type. Anybody have an idea what I'm getting at? How do you rearrange logarithms? This is a base. Well, actually, I was referring to a rule we learned previously, actually. So, like, we did this earlier today in class. This is a base right here of 2. So it's going to go 2. Then this x is going to go up top. It's going to be equal to 32. 32 is actually 2 to the 5. Therefore, this is equal to 5. That's a useful skill to have. That being said, don't forget, you can, if you know how, just literally type that in your calculator because it is a number. And the number should have also been 5. So far, so good? Say that again? 2 to the x, I just kept. 32 is 2 to the 5. And then the 2's canceled. Okay, the next rule that I want to talk about is called the change of base rule. I've actually already shown at least Brad and Emma this because your calculators don't do the little small base thing. I just never told you this is what we were doing. But if your calculator can't do that small little base, there's a rule basically that says that in order to solve this, you take the log of the big number, which is this number right here, and then you divide by the log of the little number, which is this little number right here. And that's actually another way you can work with logs. Log 10 divided by log 10 is going to be 1. By definition, anything that's divided by itself is 1. So for this one right here, if you don't know how to get that little 2 down in the bottom corner, or perhaps if you don't want to take the time to actually dig through your calculator and find that like little small base log thing in the catalog, you can just call this thing log 3, and then you can divide by log 2. Here's how I type it in your calculator, though, just to make sure you're clear. I'd go log bracket 3, close the brackets, then divide by sign, then log bracket 2. That's how you're going to want to type it in. Don't forget that little bracket sign right there, otherwise it's going to goof the whole thing up. So, the other rule that we have to work with is called the power rule. And basically the way this works is that if you ever have a number that you are logging, I think that's a good verb to use, if it can have a power, like an exponent, you can actually drop that power down in front of the whole logarithm. So let me show you an example. You guys see how this is log base 3 of 9, but 9 can also be written as 3 squared. Okay. Well, the power of a log rule means that this squared symbol right here is actually able to drop in front, and it gives you 2 times log base 3, 3. I'm going to say this a lot. What is log base 3, 3? It's just a number. Well, what I could do with this log base 3, 3 here then is say, well, that means it's log of the big 3 divided by log of the little 3. Isn't log 3 over log 3 like literally the same thing on top of each other? Kind of cancels? The answer is 2. let me show you another way we could have solved that. By the way, did that make sense, by the way? Here's another way I could have solved this. I could have said that log base 3 of 9, I'm trying to find what it's equal to, so I'm going to say it's going to be equal to x. And I'm going to solve for x. And then I'm going to use the rule I taught you guys last week. 3 goes to the power of x, and it would be equal to 9. But isn't 9 equal to 3 squared? So then doesn't this 3 and this 3 cancel, thereby making x equal 2? I just showed you how to solve this 2 different ways. The first way I solved it was using like this, let's make this 9 into a square, let's drop the thing in front and solve. The second way I showed you to solve is using rules we learned last week. You know, a third way you can solve is just literally type this in your calculator. You could type log base 3 of 9 in your calculator and get it what it's equal to. Again, this is my toolbox analogy. I don't care which method you use, but I just need you to be fluent in using any of them in case one is not helpful. Alright. Let's try the next one. Log base 3 square root 27. Do you guys remember how square roots work for exponents? A square root means the exponent is 1/2. Should write this to the side. X to the 1/2 is the square root of x. So the reason why I wanted to show you this one is this is really log base 3, 27 to a half. Why is that helpful? Well, at least in terms of one way of solving it, you can take that 1/2 and it can come in front of the whole logarithm, meaning this is now equal to 1/2 of log base 3, 27. Don't get stumped on this little bit here. Log base 3 of 27 is just a number. If you're struggling with how to put that in your calculator, you could say that it's the log of 27 divided by the log of 3. So, here, I'll use my calculator now and try to solve what this is equivalent to. I need 1/2. Then I need the log of 27. My calculator doesn't do the little base, so I guess I'll just have to do it the long way and then divide by the log of 3. The answer is 1.5. Does that make sense? What if it's the one afterwards where it's log base 3? Sorry that I'm all over the place. Log base 3, now a 4th root of 27. How does that work? Anyone remember? What does a 4th root mean as an exponent? It's a quarter, yeah. So what you could do is you could say log base 3 of 27, but now it's the power of a quarter. That's what a 4th root does. I'm just going to do the exact same thing in solving this one then. You could pull the 1/4 down in front. It would give you 1/4 log base 3, 27. And then for like what's going to be the millionth time today, log base 3 of 27 is just a number. Just need to try to find a way to type it in my calculator. So I'm going to type in 0.25 because that's a quarter. I'll times by log of the big number, 27, divided by the log of the little number, which is 3. And I got 0.75. I guess in theory you could have even done this. You could have done log. Then you could go like 4 math. You could go like 4th root of 27. And then you could divide by the log of 3. This should also give you the same answer. So, tools. I don't know. One's a hammer, one's a duct tape. I don't know. I want you guys to have multiple ways of solving things. So far, so good? It's boring? You guys look bored. Alright, moving on. Okay, how can I write this one here as a single log then? They're being added. 2 separate logs being added means collectively multiply them. So you need a log of big bracket, then a second bracket, a plus b, and then a minus b. Does that make sense? Well, that's actually what I want to do next then. What can I do inside the logarithm here then? Well, you can FOIL those guys then. That's what I was going for. So what happens when you FOIL a plus b next to a minus b? Yeah, you get the log of a squared plus b squared. Not plus, minus b squared. The log of a squared minus b squared. I want to point something out about this one here. This is not equivalent to the log of a squared plus the log of b squared. Does that make sense? Or sorry, minus the log of b squared. I don't know why you'd pick plus. Either way, it wasn't equivalent. Okay. The way the rule works is that if you have separate logarithms, you can combine them by multiplying. However, if you have a logarithm that has a minus sign in between, you can't break them apart separately. It's not something you can do. Okay, let's try this one here. How can I try to combine this one as a single log? Maybe it's just best if I show you some tricks then. Log A right here, I'm just going to leave that as log A. But do you guys see how you have the 3 in front of the log B? I can go backwards. You know how I was able to make an exponent come from up top and the exponent comes down in front? I'm going to go the other way. I'm going to take the exponent, the number from being in front, and I'm going to bring it up and make it an exponent. So now it's log B, but now the B is cubed. See how that works? I actually have the same principle right here. This 5 right here, I can bring it up as an exponent. So I'm going to add log base 5th root. By the way, what would a 5th root be as a fraction? Okay, so the 5th root makes it 1 over 5, but then I'm taking the 5 and I'm bringing the 5 up top, so I get it times by 5. What's 1/5 times 5? Yeah, just 1. So here's what I'm left with. Log A minus log B cubed plus log C, I guess to the 1 technically. Let's skip the 1. We're not done though. There's one more step. We want to write it as a single log. I can combine all of these logs together so long as I do it correctly. You see how these two logs are being subtracted? Subtracting means divide. So do the log of, in brackets, A over B cubed. And then see how we're adding log C? Adding means multiply, which means the C has to go on the top again. I want to make sure I'm really clear about this here. Because this plus C is written like that, the C actually has to go on the top of the fraction again. However, if they had written it with a bracket like this, then the C actually would have gone on the bottom instead. Do you guys see the difference there? The plus C means it goes on top. If it was like, say, a minus C, the C would actually go on the bottom with the B. Or if there had been some brackets here, you'd put both of them on the bottom.
If the brackets were where? Sorry.
Okay, so hypothetically, let's say there were some brackets right here. It means that this C, rather than being up top, would have been on the bottom. But that's not what it was. So because it was a plus C, I just want to make the note, C goes on top. C is the numerator because of the plus sign. Am I done so far? Does this make sense? Okay, let me show you a question that I've seen on a diploma exam before. It was still multiple choice, but it was a lot more difficult because you really couldn't use your calculator. And it's this part C1. Hypothetically, let's say that log base 4, 5 is considered to be what x is, and log base 4, 3 is considered to be what y is. We're going to try to write this guy in terms of x and y. I don't remember what the answers were for multiple choice, but I want to think it might have been like, say, 2x plus 2y. B might have been x plus y. C might have been 2xy. And D might have been, I don't know, x plus 2x plus 2. No, I already did that one. maybe d would have been x squared plus y squared. Does that make sense as like a question? The challenge now is, well, how do I deal with this? Because I can write one equation in my graphing calculator. I mean, I guess I could throw this in my graphing calculator. Maybe you could throw this in my graphing calculator, but I'm not really sure how that helps. Does that make sense? So here's how I would suggest solving this problem. Log base 4, 225. You know how like 225, maybe in grade 7 you learned how to like break it up based on factors? What are the factors of 225? It probably divides by 5, I'm guessing, right? 15 and 15? Okay, well then 15 is a 3 and a 5, and the other 15 is another 3 and a 5. So would it make sense for me to write this now as log base 4 of 3 times 3 times 5 times 5? So that's still equivalent to 225. This is still 225. The reason why I'm choosing to do that is now I have a whole bunch of stuff multiplied together. So I could write this as log base 4 of 3 plus, because that's what multiply does. Now I can have log base 4 of 3 again. Then I have to add log base 4 of 5, and I have to add log base 4 of 5. Does that make sense? The answer was A, yeah. Because then the rationale behind this is that this guy right here is what I told you that y was equal to. This guy is also what y is equivalent to. This guy is what x is equivalent to. That's also x. So by the time you're done, you have 2 x's and you have 2 y's. That being said, that's kind of a challenging question until someone shows you maybe how to solve something like that. Because there's really not a great way of guessing and checking that. Why don't we take a break? Because I still have quite a bit left, don't I? What was that? Oh, only one page? Oh, sorry, I thought I had lots more. Do you guys just want to finish the page and then be done?
Yeah.
Okay, why don't we do that then? Oh, yeah, okay, yeah, if I just have 2 equations left. Okay, so let's try solving these last ones then. Whenever you get evaluate, sometimes one of the things I like to recommend with evaluate is that you're trying to figure out what this is going to be equivalent to. So it's going to be equivalent to x, and in a way we're trying to solve for x. Does that make sense? So here's a possibility. This is not the only way you have to solve it, but you see how you have that 3 over 2 as an exponent? What you could do is you could drop that down in front. So then you could write it as 3 over 2 log base 8 of 2 equals x. You could, in theory, I guess, kind of take this 8 and go to the power of x and make it equal to 2. I'm not sure if that's useful, though, because I've already said this a lot today. Log base 8 of 2 is just a number. Yeah. So if you need to, type it as log of the big number divided by the log of the little number. That's what x would be. So 3 over 2 times by the log of 2 divided by the log of 8. I guess. Was everybody able to solve for 0.5 and have that make sense to you? Okay, I want to show you other ways of solving it, though. You know how way back here, I pulled that 3 over 2 down in front? Let's say that I didn't recognize that log base 8, 2 is actually just a number. Let's say I wanted to convert this using like the converting logs to exponent form. Can I do that at this point here with this 3 over 2 sitting in front? Not quite. But what I can do is I can take the 2 and put the 2 up top on this side right here, and I can divide by 3. That makes sense how I'm kind of bringing the 3 down here. Well, because now what I'll have is log base 8 of 2, and I get 2x over 3. Does that make sense? Now I can try that trick that I showed you last week. So it would be like this. 8 would go to the power of 2x over 3, and it would equal 2. The reason why this might be useful is that 8 is actually 2 to the 3. So as a bit of a brief aside here, then I could write this as 2 to the 3 times by 2x over 3. And that'll equal 2 to the 1. Does that make sense? So 8 is equal to 2 to the 3. So I'm writing it as 2 to the 3, but you see how I still have that exponent up there? I kind of just left it there. And then this 2 right here, I guess, is 2 to the 1. I can cancel the 2's. 3 times something over 3, that'll cancel as well. And what I'm left with algebraically is 2x equals 1. Divide by 2, x is another way of solving. Now, I don't know that that's the best way of solving. Well, I could have just done what I did to start with, right? Where I brought the 2 over 3 down in front, and then I just recognized, hey, log base 8 of 2 is just a number. Don't freak out, Chris. I can just type it in my calculator, right? But one of my goals today is to show you that there are multiple ways of solving, and I want you to be comfortable using more than one way. Some of my best students, Will Lamb comes to mind, if you guys knew who Will was. He would try to solve things as many ways as possible, or at least 2 ways. And if he was able to solve something 2 different ways and get the same answer both times, then he was pretty confident he had the right answer. Does that make sense? So if you have extra time, it doesn't hurt to be like, okay, I've solved it one way. Let's see that I can try solving it another way. Let's try another one here. Any thoughts? What useful skills do you have in trying to solve this, other than maybe just literally typing it straight in your calculator? Because that would work too, I guess. What does this 2 right here mean? Okay, so I could put it up top, right? So I could make this log base 2, and then rather than 12, it'd be 12 squared. So I'm just going to call it 144, if that's okay. Good, and so what we could do is we could divide this by some of the stuff that's sitting there. So one of the things I'm going to need to divide by is a 6. Because there's a 6 right here. Before I divide by the 27, see how there's this 1/3 kicking around right there, though? I have to deal with that. That 1/3 can actually come up top on the 27, making it 27 to the 1/3. Just going to do a little side note here, then. This is now 27 to the 1/3, which is the same thing as cube rooting 27. Anybody know what the cube root of 27 is? Yeah, it's 3. So essentially all of this mess right here gave me the log base 2 of 3. So I can just make it a 3, and the 3 goes on the bottom with the 6. You see how because of this big bracket right here, both of those numbers go on the bottom? Someone help me out. What's 144 divided by 18? Because 3 times 6 is 18, right? 144 over 18? 8? Now again, I could just type that into my calculator. Or here's another skill I could use. I could say, well, that is now equal to x. 2 goes to the power of x to equal 8, using like this kind of rule there. And then you could say, well, 2 to the x equals 2 to the 3, because 8 is 2 to the 3. By the time you're done, you've proven that x equals 3. Again, you could, in theory, just type this whole shebang in your graphing calculator. So long as you know how, and you do it properly, that would work too. So, like I said all class, my goal is to try to give you multiple different skills. If you just type this in your graphing calculator, you're using duct tape. It's not a bad thing to know how to use duct tape, but it also wouldn't hurt to know how to use a screwdriver. So work on other skills when you can. All right, last one, then we'll take a break. Now let's do some graphs. So one of the skills I need you guys to have is to be able to draw a graph of something. In theory, if you know how, you should be able to type all of this into your graphing calculator. It's quite a bit, though, to be able to type in. And you have to be able to interpret the graph. What I'd like to do is I'd like to use some of our log skills to simplify it, maybe before we start typing it in our graphing calculator. You have two logarithms that are being subtracted. What does that mean? Okay, so it's log with a base 5 of 2x minus 2 over top of x squared plus 2x minus 3. Hidden inside a logarithm is a rational. We're actually combining outcomes. This is where you have to know what a logarithm graph looks like, but you also need to know what rational graphs do. One of the big things on rational graphs is there's the possibility of either a hole in the graph, if something cancels, or asymptotes. Just pause for a second here. I just want to make sure everyone catches this. Because of the logarithm itself, you're going to get an asymptote. Because of the fact that inside the logarithm is a fraction, you're going to get either more asymptotes or you're going to get a hole in the graph. Does that make sense? So we're going to either have at least one asymptote and possibly more asymptotes, or we're going to have the asymptote due to it being a log and holes. So now let's try to factor this guy. Okay, so that gives you 2 with an x minus 1. Okay. Good. So based purely on not even typing this in my graphing calculator, I can tell you that I'm going to expect a hole in the graph where x equals 1. That makes sense? I'm also going to expect an asymptote where x equals negative 3. And I think there's also going to be another asymptote just due to the fact that it's a log. Now, I'm not 100% sure whether it's going to be at 0 still or not, because of the fact that all of this stuff right here does technically move the graph around a little bit. But now I'm actually going to try typing in my graphing calculator. I didn't want to do it at first, but now let's actually get a better look at it on our graphing calculator. And I'm going to recommend, let's type in the original. So if you have the ability to do the little small 5, you could do that. I'm going to do change of base because that's how my calculator works. So here's what it's going to be. Log of 2x minus 2, and then I have to divide by log 5 because that's the only way to make a base work on my calculator. If you can do the little 5, though, do the little 5. And then I'm going to subtract the log of x squared plus 2x minus 3, and then I have to, again, divide by log 5. Everybody okay so far? Okay, so now I'm going to graph this thing. We'll try to see what it looks like. Okay, we need to use a lot of, what's the right word to use here? Interpretation skills, probably the right word to use here. Because I'm not sure that the graph looks quite like this. I thought there was going to be some asymptotes, and I'm not really seeing one. Now, you know how I said there was an asymptote over here at negative 3? I feel like perhaps there would have been an asymptote if it wasn't for the fact that there's a rule about logarithms. You can't logarithm negative numbers. That makes sense? Right? Like when you do the log and you try to logarithm a negative number, negative 3, that wasn't actually allowed anyways. So although I thought there might have been an asymptote at negative 3, I don't think that really matters because, look, all of our negative numbers don't seem to work anyways. Does that make sense? As I look at my table of values, it looks like 0 doesn't work. I think that kind of makes sense because doesn't a normal log graph, like without any changes to it, basically start right at 0? Why does... Oh, you guys have something different.
Yeah.
Uh-oh.
Mine, like, it doesn't go to the 0, but it goes to negative 2 and then stops at 1 where the hole is. And then it keeps going.
Did I mistype something?
Maybe you didn't use brackets.
Yeah, maybe I should check that. because I didn't use a big bracket for everything. So the downside with using my little calculator is it doesn't show all of these things here. How about that? So that brackets those ones. Does that change my graph? Is that what you guys have? That's kind of fun. 2x minus 1. Okay, you have 2x minus 1, actually 2x minus 2. Oh, I see what you did. So you just want to divide it by 1 there. You technically, though, didn't use the original equation. But what we should really use is the original they gave.
Wouldn't that make the same equation?
I guess. So your graph should be going originally there. I think what's happening here, though, is that in this original equation right here, you can't use like a number like, say, -2, because that's going to make that be a negative, and then it doesn't work. But in this particular one, -2 still does work. I think I can explain this. Yeah, okay. Out of curiosity, are you guys, when you're typing in your graphs, are you typing in the original equation, or are you typing in this one right here?
That one, and then I typed in the original.
Okay, because you should type in the original equation, the source equation. And there is a slight difference. I think here's the reasons why. If you take a look at what x values you can't use, would it make sense to say that you can't log a negative number? Based on this equation right here, the lowest number I think I can use for x is like 1. Because 2 times 1 is 2. And then when you minus 2, it gives you 0. So like 1 is maybe the lowest number you can use for x. But like, say you look at this equation right here. You might be able to use a number lower than 1. Like say, I think -2 actually works in this equation. Because when you plug in -2, it gives you like a positive number. I guess long story short, what I'm trying to say is that use the original though. Don't use this one right here. I know that it's equivalent, but use the first one. Okay, back to answering the question then. As I look at my table of values, does it make sense that all of a sudden the graph stops at 1? As I look at numbers that I try to use, if I try plugging in 1 for x, 2 times 1 would give me 2, minus 2 would give me 0. I can't use the number 1 because I can't log 0. I can't use 0 either because 0 would be 2 times 0 would give you like 0, then minus 2. I can't log a -2. So one of the things that restricts domain and range, I think the point behind this question, I want to put a big star here, when doing domain, remember, you can't log a negative number. And that's what starts making your graph all of a sudden stop. So if some of you guys had a graph where there was like, what did Driana's, yours kind of kept going that way, correct? Yeah. These numbers right here for x, you can't use those because if you tried using those in the original equation, you'd be trying to log negative numbers. If you try logging them in this equation here, I think what ends up happening is you get a negative number on the top, you get a negative number on the bottom, and it makes it a positive number, and so then you can log it in this set of the equation, but back in the original equation you can't. Okay. So I'm actually starting to think now that even though I thought there was going to be a hole in the graph and an asymptote and a log, what ends up happening is there would have been asymptotes and holes and logs, except this whole half of the graph area, like from this point onwards, gets wiped out because you can't use those numbers because then you'd be logging negative numbers. So I'm feeling fairly comfortable with the graph just all of a sudden kind of starts right here, right after the number 1. I'm just going to test a few numbers just to see. Like, calculate the value. If I type in 1, it doesn't work. Does that make sense? What if I just don't believe my graph? What if I want to try the number 0.99, like slightly in front of it? Also doesn't seem to work. Does that make sense? What if I test it on the other side? So I can calculate the value of 1.01. Yeah, it looks like I got something there. Does that make sense? So I'm going to say for the domain, sorry this is ugly, it looks like your domain is everything bigger than 1. I don't think I can use 1 itself, but I can use everything bigger than 1. I think the harder one is going to be trying to figure out the range. Any thoughts as to how to try to figure out the range? What was that? It might be less than 0. Am I completely confident of that? Because like when I typed in 1.000001, it gave me negative 0.43. Maybe it's a little lower than 0. I have an idea. You guys know how when we needed to find a hole in the graph before, we had a method for doing that? We actually did all of our canceling, and then we plugged in 1 when we were finally allowed to plug in 1. In this original equation right here, I can't plug in 1. I'm not able to plug in 1 in the original because it'll make me log a negative number. I don't even think I can plug in 1 in this particular equation here because it's also going to require me to try to log 0, and that's not doable. But if I take this equation that I have right here, I'm just going to write it below. It was, oh my goodness. It's log base 5 of 2 over x plus 3. I know in the original equation, I can't use 1 and negative 1 and 0. Like there was a whole section of numbers I couldn't use. But in this part of the graph right here, now can I use 1? Yeah. Now I can plug in 1 if I want. So now it's log base 5 of 2 over 4, which is the same thing as log base 5 of a half. Or I guess I should take my own advice. Isn't log base 5 of a half just a number? So I'm going to log a half, and I'm going to divide by log 5. It looks like negative 0.43 seems to be about where the graph starts. And if I go back to like my calculating a value of 1.01, yeah, see how it looks like it's starting at about negative 0.43? Does that make sense? So that looks like that's the y value it starts at. So then I should say for range, y is going to be less than about 0.43 in the negative. I don't think that number itself was included because remember x itself for 1 wasn't able to be used. So in a way it's kind of like there's a hole in the graph. Like if I were to draw that graph there, there's a hole in the graph kind of starting the graph off. And I can't use anything behind that number because again in the source equation, in the very original equation, you were limited by what x was allowed to be. X can't ever be a negative number that you're logging.
How
Yes.
do you do the infinity one?
The asymptote the other way?
Yeah.
So then what you want to do is go, like say second table set, and then make it go to like a very large number. And then you go to the table and see whether it seems to be getting close to a certain number. At this point it looks like it's getting close to 12.45. I feel like though if I keep going even further and add more zeros, I think it'll keep going though. Like log graphs should keep going for forever. So that graph that I had right there, it is slowly but surely getting lower. It's taking its time, but it's getting there. So. Did that last one make sense? There was a lot in that example I was trying to show at once. Most of it though revolves around the idea of you can't just trust your graphing calculator. You have to have some ability to interpret the graph otherwise. I originally thought there was going to be a hole in the graph and a bunch of asymptotes, and I wasn't right. But the reason why I wasn't right is that this half of the graph wasn't even valid because you couldn't even use numbers in the negatives because it wasn't allowed. So, okay, I'm done. That was a long time. Any questions? Okay. Here's some pages in your textbook in case you care. I'd recommend though, keep working on that assignment. I'd like it done for Friday. Today we have Flex Friday, so you can work on it on Friday if you need. Tomorrow's our last lesson for the unit, and then Thursday we're writing a quiz. Sound good?